Note that the material from 5 minutes to 14 minutes 10 seconds in this video provides useful background information but is not required for the AP exam. This time frame includes the topics listed below. Enthalpy is potential energy that may be evolved or absorbed as heat. Delta H, also known as an enthalpy change, is the heat that is absorbed or released by a reaction. Specific types of enthalpy changes may have a subtitle attached to the delta H. Shown below is the reaction for the combustion of propane. The delta H value associated with this reaction has the subtitle combustion attached to it. Electrons in the atoms of the molecules of any substance have potential energy. This is due to the position of the negative electrons in an atom relative to the positive nucleus and the other nuclei nearby in a molecule. This potential energy that the electrons and also protons have is called bond energy. This bond energy is the energy of intramolecular bonds. Intramolecular bonds are those formed between atoms within a molecule. There are also weaker bonds that exist between molecules, and these are known as intermolecular forces. Intermolecular forces relate to the polarity or lack of polarity of molecules. The prefix intra means within, while the prefix inter means between. If you have trouble remembering the difference between these, it might help to think of the words intravenous and intermission. Intravenous means within a vein, and most often refers to giving medicines through a needle into a vein. An intermission is a break between parts of a play, movie, or concert. The difference between the potential bond energy of reactants and products in a chemical reaction is the enthalpy change or delta H value. Bond breaking requires energy input, and hopefully it's fairly intuitive that breaking something requires energy. On the other hand, bond forming results in a release of energy. A reaction accompanied by an absorption of heat is endothermic, while one accompanied by a release of heat is exothermic. In an exothermic reaction, the heat absorbed to break bonds is less than the energy released during bond formation. This means exothermic reactions have negative delta H values. The opposite is true of endothermic reactions, where the energy absorbed to break bonds is more than the energy released during bond formation. This means endothermic reactions have positive delta H values. Here we can see a potential energy diagram for an endothermic reaction. The horizontal axis is the progress of the reaction, sometimes labeled as the reaction coordinate, and on the vertical axis we have potential energy. As we can see, the potential energy of the products is greater than that of the reactants, so the change in enthalpy is positive or greater than 0. This is the potential energy diagram for an exothermic reaction. The potential energy of the products is less than that of the reactants, as energy has been released. The value of the enthalpy change is negative. There are two ways we can express the enthalpy change associated with an equation. One is known as delta H notation, which we saw earlier. This notation requires that the enthalpy change is specified with the equation, but written separately following a delta H symbol to the right of the equation. Note that the value is negative, so this is an exothermic reaction. This makes sense seeing as it is a combustion reaction. The other way we can express the enthalpy change with an equation is by writing a thermochemical equation. A thermochemical equation includes the delta H value as an integral part of the equation. In an exothermic reaction like this, we know energy has been released and this energy appears on the product side of the equation. For an endothermic reaction, the energy would appear on the reactant side. Note that the units of delta H are in kilojoules per mole. The mole here is actually referring to a mole of the reaction. A mole of the reaction depicted involves the combustion of 1 mole of propane. But what if we doubled the coefficient so that it depicted the combustion of 2 moles of propane? This would mean the energy released from 1 mole of this reaction would be twice the energy released from 1 mole of the previous reaction. Let's now do an example. Here we are given an enthalpy change value which corresponds to the decomposition of ammonia. We need to write a balanced thermochemical equation and an equation using delta H notation. When ammonia decomposes, it will become nitrogen and hydrogen. Nitrogen and hydrogen both exist as diatomic molecules. We first balance the equation, making sure we have the smallest whole number coefficients possible. There is now a 2 in front of the ammonia, but the delta H value we were given is 46.1 kilojoules per 1 mole of ammonia. We will need to place double this, 92.2 kilojoules, in our thermochemical equation. The delta H value is positive, so this is an endothermic reaction, and we place the value on the left side. We then write the delta H notation, with the delta H value separate from the equation. The origin of chemical energy lies in the position and motion of atoms, molecules, and subatomic particles. What is shown here are various types of energies that combine to give the total internal energy of a sample of matter. Earlier, we looked at potential energy due to the electron-nuclei interactions. The kinetic energy of moving electrons also falls into the category of electronic energy, though the potential energy is more significant. Let's take a look at a molecule to help illustrate the other energy types. There is kinetic energy due to the rotation of a molecule about its center of mass. This is known as rotational energy. There is also vibrational energy due to the vibrations of atoms within the molecule. Finally, there is kinetic energy associated with gas molecules as they move linearly from one place to another. This is translational energy. Thermodynamics is the study of energy changes and the laws governing the conversion of heat into other forms of energy. It is mainly concerned with macroscopic properties, which are those you can see or measure. The reaction or physical system we are studying is called the system, while the rest of the universe is called the surroundings. A state function is a property that depends on the current state of a system. It is independent of the pathway taken to reach the state. A system's volume, temperature, pressure, and composition are all state functions, as they only depend on the final and initial states, and not on the path taken to establish the state. Internal energy, enthalpy changes, as well as entropy and free energy are also state functions. On the other hand, a pathway-dependent function is a function that does depend on the pathway taken to reach the current state. Work and heat are two examples of this. Note that all forms of energy are state functions. Some people wonder why heat is not a state function. Remember that heat is defined as the transfer of kinetic energy. Hence, heat is certainly pathway-dependent and so is not a state function. This image can help illustrate the difference between state functions and pathway-dependent functions. The flashlight and car are both operated using the same batteries. The total change in internal energy is the same, yet the work done and heat radiant energy released are not the same. This shows us that internal energy is a state function, while work and heat are pathway-dependent functions. Now let's take a look at sign conventions, which will be similar to the ones discussed for enthalpy. Energy leaving or produced by the system has a negative sign, while energy entering the system from the surroundings has a positive sign. If the volume of a system decreases, the change in volume, delta V, will be negative. This should make sense considering the change in volume is the final volume minus the initial volume, and if the volume has decreased, then the final volume is less than the initial volume. If the volume of a system increases, then the final volume will be larger than the initial volume, and delta V will be positive. For now, the first law of thermodynamics is as far as we'll go with thermochemistry. The first law is really just a restatement of the law of conservation of energy. Energy cannot be created or destroyed. It can be converted from one form to another. Another way of saying this is that the change in energy of the universe is zero. It is also equal to the sum of the change in energy of the system and the change in energy of the surroundings. Two common methods for transferring energy between a system and its surroundings are heat, Q, and work, W. We can define the change in internal energy of a system, delta E, as the sum of heat and work. Work done by expanding gases is called pressure-volume work. This work is equal to the negative of the pressure times delta V. We need this negative sign so that we get the correct sign for work. For instance, if the volume of a system decreases, then we know work was done on the system and it is thus positive. But the volume change would be negative, and P times delta V would also be negative, resulting in a negative value for work, hence why we need to use negative P delta V. We want our work to be in units of joules and not liter atmospheres, which we would get from this equation, so we will need to use the conversion factor of 101.3 joules is equal to 1 liter atmosphere. In this first example, a system absorbs 401 joules of heat, while the surroundings do 252 joules of work on the system. We need to find the change in internal energy for the system. The change in internal energy is equal to the sum of heat and work. The system is absorbing heat, so Q is positive. Work is done on the system, so work must be positive. We add these together to get the change in energy. This is a positive value, which makes sense. Adding heat and doing work on the system should have increased its internal energy. Here, a system released 1.3 kilojoules of energy, as its internal energy increased by 2.1 kilojoules. First, we are asked if work was done on the surroundings or the system. Releasing heat would lower the internal energy of the system, but the internal energy has increased. This indicates that work was positive and done on the system. Calculating the amount of work involved should verify this. We can write down the equation and plug in the known values. The change in internal energy is positive, as the internal energy has increased, and since heat was released, Q is negative. The work ends up being positive 3.4 kilojoules, confirming that work was indeed done on the system. Next, if the pressure was 1.7 atmospheres and the initial volume was 38 liters, what was the final volume? We have values for work, pressure, and initial volume, so our equation for pressure work should be of use. We can rewrite the change in volume as the final volume minus the initial volume, seeing as we would like to solve for the final volume. We can plug in the values we were given and also the work we calculated earlier in the question. 3.4 kilojoules is equal to 3,400 joules, but we will want to convert this to liter atmospheres because we will need to divide both sides by 1.7 atmospheres and add 38 liters to both sides to isolate the final volume. On the right, we see that our units of joules and atmospheres will end up being cancelled, leaving units of liters. Another way we could have done this is to have solved for delta V first by dividing work by pressure, and then we would use delta V equals the final volume minus the initial volume to find our answer. The ideal gas law, which is covered in depth in the chapter on gases, states that for an ideal gas, the product of a gas sample's pressure and volume is equal to the moles of the gas times the gas constant R times the temperature. This can be rearranged to isolate R, which only changes with the units of pressure selected. In this case, our pressure is in atmospheres, and R is 0.08206 liter atmospheres per mole Kelvin. To get this value, we have just plugged in standard temperature and pressure values for a gas. 1 mole of gas at a pressure of 1 atmosphere and temperature of 0 degrees Celsius occupies a volume of 22.4 liters. Multiplication of R by 101.3 joules per liter atmosphere gives 8.314 joules per mole Kelvin. We can now convert between units of mole Kelvin to joules, which we may need to do in problems. When heat is absorbed or released from a chemical system and the external pressure is constant, it is equal to the enthalpy change of the process. Qp is the heat released or absorbed at a constant external pressure. For reactions that do not involve gases or a change in the number of moles of gas, the pressure volume work done is 0, so the enthalpy change is equal to the change in internal energy. We can see this by looking at the equation for change in internal energy. Delta H is Qp and the work is negative P delta V. After looking at the ideal gas law, we know a gas's pressure times its volume equals the moles of gas times the gas constant times the temperature. We can replace the P delta V term with the change in moles times R times T. If there is no change in moles of gas, then the equation simply becomes delta E equals delta H. This reaction's change in internal energy value is measured as 442.26 kilojoules per mole of reaction. What is the change in enthalpy? Here we are at a constant pressure, so Q is equal to the enthalpy change. We don't have values for a final or initial volume, so instead of P delta V, we can use delta nRT, since we can figure out the change in moles of gas from the given equation. Now we can rearrange the equation to isolate delta H and plug in values. There are 7 moles of gas as products, but none as reactants, so the change in moles is positive 7 moles per mole of reaction. Delta E was given in kilojoules and not joules, so we need to multiply our R value by a factor of 1 kilojoule over 1000 joules. The temperature is given as 298 Kelvin. Note that if we were given a value in degrees Celsius, we would need to convert it to Kelvin since R is in terms of Kelvin. We now have 2 values in kilojoules per mole of reaction, so we can add them, giving us the value of the enthalpy change. The standard enthalpy of formation, abbreviated as delta HF0, is the heat of reaction for a chemical change involving the formation of a compound from its elements in their standard states. These values can be found in tables. Standard state conditions are symbolized by a superscript O and indicate traditional standard ambient temperature and pressure conditions of 25 degrees Celsius temperature, 1 atmosphere pressure for gases, 1 mole per liter concentration for aqueous species, and the physical state or phase the substance exists at under these conditions. There are a number of methods for calculating overall enthalpy changes, and the 3 most common are the law of Hess, the use of tabular heats of formation, and the use of bond energies. We will go through each of these. Recall that enthalpy is an extensive property, so the magnitude of an enthalpy change for a chemical reaction depends on the quantity of material that reacts. Let's take a look at the oxidation of sulfur dioxide gas. If the amount of reacting material is doubled, twice the amount of heat will be released. In other words, the heat released per mole of this reaction will be double that per mole of the above reaction. If the reaction were to be reversed, then the magnitude of the enthalpy change would stay the same, but the sign would change. Also remember that enthalpy is a state function, meaning an enthalpy change is completely independent of the pathway followed to accomplish it. This allows us to determine the overall enthalpy change for any reaction by manipulating a series of other reactions and adding them together. This process is known as the law of Hess, or Hess's law of heat summation. Now let's try an example. We need to use the law of Hess to determine the enthalpy change for the following reaction, using the information provided. Essentially, we need to manipulate these equations and add them together to get the overall reaction. We can begin by looking for species that appear as reactants or products in the overall reaction, which can tell us whether a reaction needs to be reversed or not. Then we can consider the coefficients of species that appear in the overall reaction, which can tell us whether a reaction needs to be multiplied. First, we might notice that methane appears only in one reaction and as a product. However, it is a reactant in the overall reaction, so we will need to reverse the first reaction. This will change the sign of the corresponding enthalpy change. Additionally, hydrogen chloride gas is a product in the overall reaction and shows up in the third reaction as a product. The coefficients are different though. There are 4 hydrogen chloride molecules in the overall reaction and only 2 in the third reaction, so we should multiply this reaction by 2. We must also multiply the enthalpy change by a factor of 2. Next, we notice that carbon shows up in reaction 1 and 2, but not the overall reaction. Hydrogen shows up in reaction 1 and 3, but doesn't appear in the overall reaction either. This indicates that they must be cancelled out when we add the reactions together. However, we see with the equations how they are now, the carbon and hydrogen each cancel, so we don't need to do any more manipulating. Summing these 3 equations with the appropriate algebraic cancelling gives the correct overall equation. We add the enthalpy values for the 3 reactions to give us the enthalpy change for the overall reaction. Another way to calculate an overall enthalpy change is using heats of formation. Heats of formation reactions for each of the compounds involved in a chemical change may be rearranged using the law of Hess to calculate the overall enthalpy change for the process. A very useful algorithm may be used to calculate the overall enthalpy change for any reaction. In fact, this calculation form will work for any state function, so we sometimes refer to it as a state function algorithm. The overall enthalpy change is equal to the sum of the product's heats of formation times their coefficients in the balanced chemical equation, minus the sum of the reactants' heats of formation times their coefficients in the balanced chemical equation. The symbol before the n in the equations is called sigma and means sum of. The n is the coefficient of each species in the balanced equation, or in other words, the moles of each species in the balanced chemical equation. Note that the standard heat of formation for a pure element in its standard state is always equal to 0. Also, the state of a substance does affect its enthalpy of formation value. Now for an example. Here we need to determine the enthalpy change for the following reaction using heats of formation. If we aren't given the heats of formation, we will need to get them from a table. We can list the heats of formation for each species in the overall reaction. Note that in the overall equation we have oxygen in its standard state, which has a heat of formation of 0. Also, be aware that there is a heat of formation for water in its liquid and gaseous state in the table, and they are not the same value. Water is liquid in the overall reaction, so we will use the heat of formation for liquid water. Now we can write down the algorithm and start putting in values. We multiply products and reactants by their coefficients in the overall reaction, and subtract the sum of the products from the sum of the reactants. The final answer can then be written down. Writing all this down with the correct units may seem tedious, but it's important to show our work properly. If we wanted to, we could omit the oxygen, since its heat of formation is just 0. Using bond energies is the final method we will use for calculating enthalpy changes. Bond energy is the enthalpy change required to break a given bond in 1 mole of gaseous molecules. It's always positive and expressed in units of kilojoules per mole. The bond energy of a particular bond between 2 atoms will vary depending on the chemical environment the bond is in, what other bonds are adjacent to it, and what lone pairs and bonding pairs of electrons are nearby. Because of this, the bonding energies typically reported in tables are average bond energies. When we look at a number of different bond energies, we notice patterns. Bond length increases with the atomic radius of each atom involved in the bond. Greater bond lengths result in less energetic and thus weaker bonds. The bonds between hydrogen and members of the halogen family illustrate this well. Another pattern is that bond energies depend on whether the bond is single, double, or triple. Triple bonds are the most energetic and hence the strongest, while single bonds are the weakest and least energetic. Since bond energy is a state function, we can use a simple algorithm for calculating enthalpy changes using bond energies. Notice how the products and reactants occur in the opposite order compared to the calculation of enthalpy from heats of formation, as we have bonds broken first and then bonds formed. Confusion with this often leads to students making errors. Knowing that bond breaking requires energy and bond forming releases energy can help us know if our sign choices make sense and prevent these mistakes. Here's an example of a problem where we must use bond energies to find the enthalpy change. Structural formulas are very useful for these questions, and if they aren't provided, we would need to draw them ourselves. However, luckily for us, they are given in this particular question. We can begin by writing down the algorithm. The formed bonds are what is being subtracted, which should make sense if we think about this a little more. Bond formation releases energy, so these values should all be negative in our equation. Bond breaking requires energy input, on the other hand, so the bonds broken should be positive values. The bond energies aren't given in the question, so we will need to get them off of the table. We will multiply the bond energies for each bond type by the number of that type of bond. We will treat this reaction as if all the bonds on the left side were broken and all the bonds on the right were formed, but we don't always have to do this. 3 carbon-hydrogen bonds, 1 carbon-oxygen bond, 1 oxygen-hydrogen bond, and 1.5 oxygen-oxygen double bonds are broken. We add these bond energies and subtract the bond energies of the 2 carbon-oxygen double bonds and 4 oxygen-hydrogen bonds that are formed, giving us our final answer. Writing down all of this can be tedious, and students frequently make errors using the algorithm as we talked about. Fortunately, there is another method we can use which is shorter and shouldn't risk as much confusion. This way involves listing all the bonds broken on the left and the formed bonds on the right. We multiply the bond energies by the number of bonds in the equation. We can then add them up for both columns. The value on the left for the broken bonds is positive, as breaking bonds is exothermic. We place a negative sign in front of the value on the right, because bond formation is exothermic. We simply add these two values to get the enthalpy change for the overall reaction, giving the exact same answer we got using the other method. Temperature is a measure of the average thermal energy in a sample of matter, while heat is the energy transferred from one body to another because of a difference in temperature. Heat capacity is the quantity of energy required to change the temperature of a particular sample of material. It is symbolized by an uppercase C and in units of joules per degree Celsius. Specific heat capacity, symbolized by a lowercase c, is the quantity of heat required to raise the temperature of a specific quantity of a substance by 1 degree Celsius. It is in units of joules per gram Celsius or calories per gram Celsius. Note how the specific heat capacity depends on the amount of a substance while the heat capacity does not. One value we will use quite often is the specific heat capacity of liquid water, which is 4.18 joules per gram Celsius. The specific heat capacities for ice and steam are also listed and are both smaller than the heat capacity of liquid water. The high heat capacity of water is actually responsible for the relatively constant temperature of coastal and island cities. Let's quickly review changes of state. In a solid, molecules vibrate but can't change place. In a liquid, the molecules slide off each other. In a gas, molecules move randomly throughout their container. To change state such as this, energy is required to overcome the attractive forces holding the substance's molecules together in the solid or liquid state. These are the attractive forces known as intermolecular forces. The energy required to overcome intermolecular forces is called the heat of fusion or vaporization, depending on whether a substance is undergoing melting or evaporation. The heat of fusion is the quantity of heat required to change a particular quantity of a pure solid at its melting point into a liquid. For water, it is 334 joules per gram. The heat of vaporization is the quantity of heat required to change a particular quantity of a pure liquid at its boiling point into a gas. The temperature remains constant during a change of state, as all energy is being used to overcome the intermolecular forces between particles. This means that the heats of fusion and vaporization are independent of temperature change, since there is no temperature change. During cooling, heat is released as intermolecular forces are formed. The magnitude of the energy in the change is the same, but is given a negative sign since energy was released. The heat of condensation is the energy released by the phase change from gas to liquid, while the heat of solidification is the energy released by the phase change from liquid to solid. A heat change that occurs at a constant temperature is referred to as latent heat. We can calculate the amount of heat absorbed or released during a cooling or heating process using the specific heat capacity, the mass, and the temperature change. For a state change, only the mass and the heat of fusion or vaporization need be considered as there is no temperature change. Here we are asked to calculate the heat required to completely melt a 1.85 gram piece of aluminum wire beginning at a temperature of 15.5 degrees Celsius. The melting point of aluminum, its heat of fusion, and its specific heat capacity are all given to us. It can be helpful to represent the energy changes with a sketch, such as this. We know there will be heat required to raise the solid aluminum to its melting point, and then there will be heat required to melt all of it at this constant temperature. Let's calculate the heat required to reach 660.3 degrees Celsius, which we will call Q aluminum. We can calculate this using the mass of aluminum, its specific heat capacity, and the temperature change. The next amount of heat needed, Q fusion, we can get by multiplying aluminum's heat of fusion by the mass of aluminum. These two values can then be added together to give us the total amount of heat required. Note that we keep extra digits for Q aluminum and Q fusion, but they were only good to 3 significant figures. When adding or subtracting, our final answer should be rounded to the least precise place value, in this case to the nearest 10. We can also do calculations where something hot is added to something cold. Here, a block of ice has been added to steam, and we need to find the final temperature of the system, assuming the final result is water. In this case, it can be really helpful to draw out a sketch first, because there is a lot more going on in this problem. The ice begins at negative 44.5 degrees Celsius, melts at 0 degrees, and continues to heat up until the final temperature is reached. We only know that the final temperature falls between 0 and 100 degrees Celsius. We don't know what it actually is, so we will just represent it as T final. To the left of T final, we have Q cold, and to the right we have Q hot. All temperature change values should end up being positive, and we need to set them up this way. Now, when we add something hot to something cold, we can use a generalized version of the first law of thermodynamics. Heat lost plus heat gained is 0. If we rearrange slightly and take absolute values, we have Q cold equals Q hot, where Q cold is the total heat gained by the colder substance, and Q hot is the absolute value of the total heat lost by the hotter substance. Q cold includes the heat required to raise the temperature of the ice to its melting point, the heat required to melt the ice, and the heat required to raise the water from the ice from 0 degrees to the final temperature. Q hot includes the heat released as the steam goes from 125.5 degrees Celsius to 100 degrees Celsius, the heat released as it condenses into water, and the heat released as this water goes from 100 degrees to the final temperature. Now we will need to calculate the heat required to cause each change. We can first set up the expressions and then substitute the values into them. In addition to different temperature values, there are different masses to keep track of, the mass of the ice and the mass of the steam. We will carry our work over and begin to do a bit of algebra. We know our final answer will be in degrees Celsius, so we have opted not to show units here for clarity. Everything has been multiplied out so we can isolate the like terms. Our final answer should be good to 3 significant figures based on the precision of the values in the problem. We use this for sig figs rather than each step in the algebra, since sig figs apply to measurements, not algebra. Most people are familiar with the calorie as it appears on the label of virtually all prepared foods we purchase in supermarkets today. The caloric content on these labels is in calories, or big C calories. One of these big C calories is equal to 1,000 calories or 1 kilocalorie or 4.184 kilojoules. But how do we measure the value of food's caloric content? To do this, we can use a device called a calorimeter. This is an example of a coffee cup calorimeter. There are 2 styrofoam cups, one nested inside the other, which provides reasonable insulation. The principle behind the calorimeter is the law of conservation of energy. Heat lost or gained by a physical or chemical change in the calorimeter equals heat gained or lost by the system, usually an aqueous solution, inside the calorimeter. There is a thermometer to measure the temperature and also a stirrer. The temperature change produced in a given mass of aqueous solution can be used as a measure of the amount of heat produced or absorbed during a physical or chemical change occurring in a calorimeter. If the change is exothermic, energy is released and the temperature increases. If it is endothermic, energy is absorbed from the water and the temperature decreases. Over here, we have a commercial calorimeter, which is similar but a bit more sophisticated than the coffee cup calorimeter. These may consist of an inner and outer vessel, separated by airspace to provide better insulation, an insulated lid, a stirrer, and a simple thermometer. Now let's go ahead and look at an example. When 500 milliliters of 2 molar barium nitrate solution and 500 milliliters of 2 molar sodium nitrate solution, both at 22.5 degrees Celsius, are combined in a coffee cup calorimeter, the temperature of the mixture rises to 25.6 degrees Celsius. Calculate the molar enthalpy of precipitation of barium sulfate. We start by writing down the balanced chemical equation. We will want to know how many moles of barium sulfate are produced, but this depends on the moles of the reactants. The reactants are present in equimolar quantities, so neither is in excess and we can assume both will be consumed completely. There is a 1-to-1 mole ratio between barium sulfate and either of the reactants, so 1 mole of barium sulfate is produced. Next, we want to find the heat absorbed by the resulting 1 liter solution, and we write down our equation. We are assuming the solution has the same density and specific heat capacity as water. Note we are using 1 liter and not 500 milliliters because we combined two 500 milliliter solutions. Heat lost equals heat gained, so the heat absorbed by the solution must equal the heat released by the reaction. The reaction takes place at a constant pressure, so the heat released is equal to the enthalpy change for the reaction. We want the molar enthalpy of precipitation of barium sulfate, so we divide this value by the moles of barium sulfate that formed. However, we are not done yet. We need to make sure the sign of the enthalpy change is correct. This isn't something we want to forget to do. In this case, heat was released from the reaction, so the reaction was exothermic and a negative sign should be added. We could have added in the correct sign earlier, but it is easier not to get lost in the algebra if it is added conceptually at the end. A bomb calorimeter is more sophisticated than a coffee cup or thermos type calorimeter. It's often used to determine the heat change involved in a chemical reaction, including reactions such as combustion reactions which don't occur in solution. They measure the heat released at constant volume, which is extremely close to delta H. The reaction chamber, which is surrounded by a metal jacket, sits inside a known mass of water at a known temperature. A crucible containing the substance to be tested or burned sits inside, and a spark or electric current from a DC source supplies the activation energy to initiate the reaction. Prototype bomb calorimeters had extremely precise thermometers extended from inside the bomb with a sliding magnifying lens to assist in reading the temperature to the 3rd decimal place, while modern calorimeters may use a digital one. There is a mechanical stirrer to ensure the temperature is evenly distributed throughout the solution. Additionally, oxygen would be added to the reaction chamber before it is placed in the solution. Sometimes calculations involving bomb calorimeters require an overall Q or delta H value to be determined by individually calculating a value for the water inside the calorimeter, and a value for the metal jacket using the specific heat capacities and the masses of each. Other times, an overall heat capacity in units of joules per degree Celsius may simply be used for the entire calorimeter, which is sometimes called a calorimeter constant. It indicates the number of joules the entire calorimeter must absorb or release in order to change its temperature by 1 degree Celsius or Kelvin. Now we will do a calculation involving a bomb calorimeter. A chunk of coal, which is just carbon, was burned entirely to produce carbon dioxide in a copper bomb. We are given the mass of the bomb and the mass of the water it was immersed in. During the reaction, the temperature of the system increased from 21 degrees Celsius to 29.3 degrees Celsius. We are asked to calculate the heat of formation of carbon dioxide. After writing down the combustion reaction, we can see that there is a 1-to-1 mole ratio of carbon to carbon dioxide. We next need to find the heat absorbed by the calorimeter bomb and the water. The temperature changes are the same for both, but their masses and specific heat capacities are different. If the values for specific heat capacities aren't given, then we get them off of the table. The two values can be added to get the total heat absorbed by the bomb and the water, which is equal to the total heat given off by the combustion reaction. To calculate the magnitude of the enthalpy change, we divide this total heat value by the mass of the carbon and multiply it by the molar mass of carbon. As we saw from the balanced chemical equation, there is 1 mole of carbon dioxide for every mole of carbon. The reaction was clearly exothermic as it raised the temperature of the water and the bomb. Thus, the enthalpy of formation for carbon dioxide should be a negative value. Notice how in this calculation we had to calculate the heat absorbed by the water and copper bombs separately. This is not always the case. A variation of this problem could provide the heat capacity of the bomb calorimeter itself. In this case, we get the heat absorbed by multiplying the heat capacity by the temperature. No mass is required. We can also see that we don't need mass just by looking at the units of the calorimeter constant. After finding this value, we would then carry on and find the enthalpy change as we did before. Another kind of problem we could get is where we are given the enthalpy change for the reaction and need to find the final temperature of the bomb calorimeter. We would first calculate the heat absorbed by the calorimeter using the mass of carbon and the heat of formation of carbon dioxide. We then know that the heat absorbed by the calorimeter is equal to its heat capacity times the change in temperature. We then substitute in values and do some algebra to solve for the final temperature.